Hi everyone, and welcome to this short video about dimension, kernel, and rank. As the name already suggests, we will talk about the concepts dimension, kernel, and rank. These concepts are highly connected with vector spaces, with matrices, and with linear mappings, and therefore you should already bring a general understanding of those. We will start with the concept of the dimension of a vector space and look at some special cases. After that, we will talk about the kernel of a linear mapping. In the end, we will cover the concept of a rank, including the rank of a matrix, the rank of a linear mapping, and the rank nullity theorem. Throughout this video, there will be several examples and exercises for you to train your newly learned knowledge. With that being said, let's start. The definition of the dimension of a vector space goes as follows. Let K be a field and V be a vector space over the field K. We call the number of vectors in the basis of V the dimension of the vector space V. And we write for the dimension of the vector space V dim of V. Here you can see two examples. The dimension of the vector space R2, so the real numbers in a two-dimensional space, is 2. And the dimension of R3 is 3. The crucial part here is the basis, as stated in the definition. So we want to know the number of vectors in the basis. You should know by now what a basis is from the video about basis from last week. And a basis for the R2 would, for example, be the vectors 1, 0 and 0, 1. So therefore, this basis has 2 elements, and therefore the dimension of the vector space is 2. And for R3, this is the same. So a basis would be 1, 0, 0, 0, 1, 0, 0, 0, 1. So 3 elements are needed in the basis. Therefore, the dimension of R3 is 3. Let us quickly go through some terminology. We say finite dimensional for a vector space that has the dimension n, with n being a natural number. So basically, if the dimension is finite, we say it's a finite dimensional vector space. We say that a vector space is infinite dimensional if the dimension is infinity. So if we cannot express the dimension of this vector space with a natural number. A one-dimensional vector space has a special name, namely a straight line, or simply line. You can imagine it like this. If you are in a one-dimensional vector space, all the vectors from this space are on one line, so you can move along one line, and this is all the vector space. If you are in a two-dimensional vector space, you call this a plane, because you kind of move on a two-dimensional plane, and everything that is on this plane belongs to the vector space. Now onto some important properties of the dimension of a vector space. They should make the general understanding of this concept and its relation to others a little bit clearer. Let's assume we have a vector space called V, and we know that this vector space V has the dimension n. Then the following 4 statements hold. First of all, every set of vectors from V that is linearly independent has at most n elements. It cannot have more elements because then at least one of them would be reproducible by a linear combination of the other vectors. The second statement here is that every set of vectors from V that is linear independent and consists of n vectors is a basis of V. This is the case because if we have n linearly independent vectors, they span an n-dimensional room, which is exactly the dimension that our vector space has. And because they are all linearly independent, they are a basis of V. The third statement is that every spanning set of V has at least n elements. It needs to have at least n independent vectors to span an n-dimensional room. It can also have more vectors, but then they wouldn't be linearly independent anymore. The last statement is that every spanning set of V that has exactly n elements is a basis of V. This becomes clear with the other statements together. A set that spans the vector space V has to have at least n elements. Otherwise, it couldn't be possible that it spans an n-dimensional space. If the spanning set has exactly n elements, this means that they are all linearly independent and that they are therefore a basis of V. Because the dimension of a vector space is such an important concept, here are some more things worth to mention. If we have some field K, then the dimension of this field K to the power of some natural number n equals n. You saw this in the beginning. For example, R3 has the dimension 3, and R2 has the dimension 2. The last two statements here are concerned with linear subspaces in dimensions. The first one states that if we have a vector space V and a linear subspace of this vector space, called U, then the dimension of U is smaller or equal to the dimension of V. So the dimension of a linear subspace cannot be bigger than the dimension of its superspace. And actually, if the dimensions are the same, then the two vector spaces are also the same. Otherwise, the dimension of the linear subspace will always be smaller than the one from the original vector space. In the last statement, we are given a vector space V and two linear subspaces of this vector space called U and W. In this case, the following equation holds. The dimension of the addition of the two vector spaces plus the dimension of the intersection of the two spaces is equal to the dimension of the one subspace plus the dimension of the other subspace. The addition of two vector spaces means that we take them together in the sense that if an element is in one of the subspaces and an element is in the other subspace, then the addition of these two elements is in the space resulting from the addition of these two vector spaces. This formula can be useful sometimes when you only know some of the dimensions and want to determine the other ones, but it is not a formula that you need to know by heart. After so much content about dimensions, let us continue with kernels now. The definition for the kernel goes as follows. Let K be a field and let V and W be vector spaces over this field K. Let phi, which maps from V to W, be a K-linear mapping. We call the kernel of phi, which is defined as phi to the power of -1 of 0, which is the set of all vectors V which come from the vector space V, for which it holds that phi of V equals 0. So we call this the kernel or the null space of phi. This looks a bit complicated, but we can tackle this together. Here you can see the formula for the kernel again. It looks a bit complicated, but you can see on the right side of the formula that the kernel is all the vectors V which come from the vector space V, for which it holds that phi of V equals 0. So the kernel contains all the vectors which map to the 0 vector. So all the vectors for which if we plug them into our mapping, this will map to the 0 vector, which is just denoted as a 0 here. And it also holds that this kernel is a linear subspace of V. This figure is to give you some visual intuition of the linear mapping and some terms related to it. So we have phi, which is a linear mapping, and it maps from the vector space V to the vector space W. So all vectors from the vector space V map to something in W. And this part in W that is hit by all of the vectors through the mapping, this is called the image of phi. And the kernel of phi are all the vectors from the vector space V which hit the 0 vector in W. And the 0 vector is also part of the image of phi because it can be hit by vectors. Here I prepared an example for you to calculate the kernel of a linear mapping and to show you this within an example because the formula looks quite complicated. So the formula here is on top again, and the linear mapping we are considering is phi, which maps from R3 to R3. So it takes in a three-dimensional vector, x, y, z, and maps via this transformation with the matrix to the vectors in R3 again. So to calculate the kernel, we want to search for all the vectors x, y, z, such that this mapping will project or map to the 0 vector. And you can try to solve this on your own now if you already have an idea how to do so, but otherwise we will also go through the solution together on the next slide. On the top left, you can see again what we were given. So we have this linear mapping and we want to hit the 0 vector by it. For the calculation, we simply fill this into a system of linear equations. So we have the transformation matrix on the left side and the solution, which is the 0 vector, on the right side. And what we do now is that we bring it to the reduced row echelon form in order to find out the solution. So we want to find all the solutions with which we can hit the 0 vector. So I won't read out all the steps in detail, but basically we go downwards on the left side and then to the right on top, and this is already where we ended up with. So you can see that the last row is a 0 row. And from the other 2 rows we can take these equations, which basically means that we have from the first row 1 times x plus 2 times z equals 0, and from the second row we have 1 times y plus 1 times z equals 0. And this leads to x equals minus 2, 0, and y equals minus 0, and z equals simply z. So we can use any z here actually. And therefore the solution for the kernel is that the kernel of phi equals z, or any variable that you could name here, times minus 2 minus 1, 1. And this holds for any z that is an element of the real numbers. And the dimension of this kernel would be 1, because it is a one-dimensional kernel, because it only depends on one parameter, which is denoted as z here. Let us continue with the concept of ranks now. And first of all, we will start with the rank of a matrix. The definition is as follows. We have some matrix called A, and the dimension of the vector space that is spanned by its columns is called the column rank of A. And the column rank of the matrix is equal to the number of linearly independent columns that it has. And now we could do the same for the rows. So if we would have a matrix A, we would call the dimension of the vector space that would be spanned by its rows the row rank of A. And the row rank of the matrix is then equal to the number of linearly independent rows it has. What is interesting now is that it always holds that the column rank is equal to the row rank. And therefore we simply use the term rank and say that the rank of a matrix A is the number of the linearly independent rows or columns that it has. And for the rank of a matrix, we'd write rank of A. The rank is a concept that is very important and quite often used in linear algebra, and therefore I want to talk about some important properties and terminology. First of all, if we have an M times N matrix, then the rank of this matrix cannot be bigger than the minimum of M and N. So it is smaller or equal to the number of its rows and columns. And we say that a matrix has full rank if its rank is exactly this minimum. And we say that it is rank deficient if it's smaller than this minimum. Calculating the rank of a matrix is actually not that complicated. There are 2 things that you need to do. First of all, you need to bring the matrix into the row echelon form, or the reduced row echelon form. And then you simply have to count the non-zero rows that it has. This sounds quite easy, so let's practice this in an example. Suppose you are giving the following matrix A. you can use the rules from the last slide to calculate its rank. And therefore you can use all the usual rules for solving systems of linear equations or for transforming matrices. You can pause the video now and then we will go through the solutions together on the next slide. Here you can see the solution for the given exercise. We start with the given matrix on the top left. Then we use the usual rules for systems of linear equations to bring the matrix into the reduced row echelon form. In the first step, we subtract 4 times the first row from the second row so that we will have a 0 in front there. Then we subtract 3 times the first row from the third row so that we also have a 0 in front. You can already see that we have a duplicate here. If we subtract the second from the third row, this will result in a 0 row. Now in the last step we can multiply the second row with -1 so that we have a 1 in the second position. You can see here that we have 2 rows which are non-zero rows, the first one and the second one. Therefore the rank of this matrix is 2. Let us continue with the rank of a linear map. As you have just learned, the rank of a matrix is the number of linearly independent rows or columns it has. But now, if we have a linear mapping, there's a different definition. Let's assume we have some field K and some vector spaces V and W over the field K, and we have a linear mapping phi, which maps from V to W. V is a finite dimensional vector space. We call the dimension of the image of phi the rank of phi. We denote it simply by rank of phi. So the image of phi are all the vectors in W which are mapped onto with phi. And the dimension of this image is called the rank. A very cool theorem that I want to talk about now is the rank nullity theorem. Let's assume we have a linear mapping phi, which maps from V to W with the same conditions as on the last slide. Now, the rank nullity theorem states that the dimension of V, which is the finite vector space we map from, this dimension is equal to the dimension of the kernel of phi plus the rank of phi. And the rank can also be expressed as the dimension of the image of phi, like on the last slide. Then we would have dim of phi equals dim of the kernel of phi plus dim of the image of phi. It is called the rank nullity theorem because the dimension of V can be calculated from the rank and the nullity. So the rank is directly visible in the formula by rank of phi, and the nullity refers to the dimension of the kernel of phi. This formula is super useful when you only know, for example, 2 of the components, because then you can easily calculate the third one. And that's already it with this week's video about dimension, kernel, and rank. By now you should be familiar with all of the 3 concepts and how they relate to matrices, vector spaces, and linear mappings. You should also be able to calculate dimension, kernel, and rank on your own. I hope you liked this video and see you again next time.